This is a great example when we need to find a global maximum or global minimum of the function in 3D with respect to the restricted domain in 2D. So I use Wolfram Alpha to sketch the graph for you. This is kind of curtain-looking function floating in 3D. And we want to find the maximum, global maximum, but only on this domain. That is my restriction, restricted domain, restriction. X values should be less than 1 by absolute value, and Y values the same thing. Maybe it's easier for you to imagine if you write down that X should be between -1 and 1, and Y should be between -1 and 1. So that's my restriction. From all the points, I have to have this restriction. Wolfram Alpha actually gives you the answer for this problem, by the way. You will see. So let's try to get the same answer as they have. As you can see, they all did all the work. There's no global... let's see. Maximize the function on this domain. And here how it looks like. Here's the heat map if you want a contour map. So let's do that by hand. Step 1, we always start with sketching the graph. So the 3D graph probably hard to sketch, but a 2D graph gonna be extremely important for the global maximum problems, X and Y. So X should be between -1 and 1, and Y should be between -1 and 1. That gives me a square. That means that while there is a curtain floating in the air, it might have its own maximum minimums going on. We want that curtain to be only considered above this square, which has coordinates from -1 to 1 on the x-axis and from -1 to 1 on the y-axis. That's kind of the idea here. This square has edges. So again, the curtain is like over here floating in the air, and it has a shadow everywhere on the floor, but we only need the shadow above the square. Global maximum might occur somewhere in between here or on the edges of the square. So that's why the global maximum minimum problems are long, because you have to consider everything in between. These points are coming from critical values, and then on the edges. So we're gonna have to make a list. To get critical points first, which might occur between those borders, you need to find partial derivatives with respect to x and with respect to y. With respect to x, it's going to be 6x plus 20xy. With respect to y, it will be 16y plus 10x squared. Now you know what to do. Set each be equal to 0. Solve this system in any way you know how to do that. I will choose here. Should I factor x and see what's going to happen? I actually should. If I factor 2x, doesn't really help so much, so let's just factor x. 6 plus 20y gives you 0. I right away have x equals 0 and y equals moves. So it's going to be -6/20, right? Looks like correct to me. Plug 0 into the second equation over here. Plug into 2. Let's call this 1 and 2. And you will have y is 0 as well. So one of the points is 0, 0. That is my critical point number 1. Unless it's not in a domain though. So make sure, I'll put a question mark. Maybe it's outside of the restricted domain. Plug this y, -6/20, into equation number 2. And you will have 16 multiplied by -6/20 plus 10x squared equals to 0. X squared, okay, 10x squared is 6 Well, let's simplify. Divide by 4, it will be 4 and 5. So it's going to be 24 over 5. X squared is going to be 24 over 5 divided by 10. Let's simplify even more. Divided by 2, that will be 12. Divided by 2, that will be 5. So that's going to be 12 over 25. X will be plus or minus square root of 12 over 25. Don't forget the negative sign, because when you do that, some panda is crying because you forgot the negative sign. So don't make the panda cry. We have two solutions here. Plus and minus square root of 12 over 25. Again, question mark, are those critical points or not? So to do that, we actually can check if these points are between -1 and 1, and they are. So yes, in the domain x is between -1 and 1, y is between -1 and 1 over here, and this 0, 0 is obviously between -1 and 1. So we have two candidates coming from the critical points 0, 0, and actually more than 2, 3. We have positive square root of 12 over 25, comma, -6 over 20, and negative square root of 12 over 25, comma, that should be like the huge square root, -6 over 20, like so. Those are my candidates. Critical points are candidates. Critical points, candidates. Now the longest step starts. I don't know, that was step 2. Okay, fine. Step 3. Step 3, check for mean max, where we're looking for the max, on the boundaries. And that is a square. So remember, we have a graph. That's why 2D graph is extremely important. From -1 to 1, from -1 to 1. We need to check the borders of each side. And we have 4 sides here. So let's call this L1. L1 can be described as x equals to 1, but then the line will be infinite, right? So we need to stop it somewhere. And then y will be moving only from -1 to 1. And that's how you describe a segment. This is called a segment. So, case 1. Segment number 1, L1. X is a number, y is a variable that is running up and down from -1 to 1. Thus, we can plug into the original, plug x equals 1 into f, the very original function, 3D function. 1 is fixed, y is a variable. So I'm going to the very original function, this one, and plug x equals 1. It will give me 3 plus 8y squared, and so on. Let's write down 3 plus 8y squared plus 10y plus 9. I would actually rewrite again the whole function because we need it. We're going to be needing it quite a lot right now. So 3x squared plus y plus 8y squared, f x comma y equals 3x squared plus 8y squared plus 10x squared y plus 9. Put in the fat rainbow box because we'll be plugging here quite a lot of stuff right now. So this is my 3D function. This is my 2D restricted domain. That's the interesting idea. So we need to plug this into this. How interesting, right? Because we're restricting the 3D picture. So here's my restricted domain for the L1. That is my case 1. And what I'm doing here, I'm optimizing now only for this function, right? So I need to find a derivative of f with respect to, well, in this case, y. It's only y here. So I don't even have to write down partial derivative. It's going to be 16y plus 10. Third equal to 0. So this is calc 1. This is optimization in 2D. Again, we did it before in different video, right? So we know how to do that. Set it equal to 0 or D and E. Solve for critical points. Minus 10 over 16 is the point I got here, which you can simplify to the minus 5 over 8. So we got this one. Now, case 2. So x is fixed 1. Y gave me minus 5/8, just for you to understand. Case 2, let's fix this to be called L2. How to describe L2? L2, y now is fixed, but x is running between minus 1 and 1. So L2 is y is fixed on the height 1, but x is keep running from minus 1 to 1, and that describes segment L2. Again, plug into the original function. X now is not fixed, but y is fixed. The original function is located in the rainbow box. Here it is. 3x squared plus 8 plus 10x squared. That's what I got. Plus 9. Differentiating this one, no need to do partial derivatives, it only depends on x. Gives you, we could collect 3x squared and 10x squared. Will give you, we could collect everything actually. 13x squared plus 17. So it's going to be 26x equals to 0. X is 0. One more candidate. We will be checking all of them later. So x is 0, y is 1. And keep going really fast. Case 3, L3. Which one would you like to call L3? I'll go counterclockwise. So let's call this to be L3. I will describe it as x equals minus 1. And then y runs from minus 1 to 1. So it's going to be x is fixed, but y is keep running. Then we repeat the whole process, plug it into the original function, minus 1 and y. Is there anything different? Because we had squares. Oh, it looks the same, because we already plugged 1, but when you plug minus 1, it will get squared. So we're going to have the same solution as L1. L1, we had x equals 1. So, same as L1. We got the same point, no need to investigate that. Finally, last case, 4. The last case, L4, can be described as y equals minus 1. But x is running from minus 1 to 1. That's the last one we did not do yet. L4 can be described as y is fixed height minus, has a fixed height minus 1. X is running between minus 1 and 1. Plugging into the original function, x is changing, y is minus 1. Fixed. 3x squared plus 8 plus 10x squared plus 9. That comes from the rainbow box. I don't even see it anymore. Oh, I accidentally changed the colors. So see, let me put the rainbow box again over here. And then L2 L3, L4, L1. So we need to solve the last derivative here. Let's simplify. This derivative gives me, that looks very familiar to be honest, 13x squared. Oh, it was a little bit different, plus 17, right? Oh, I see, it's minus 10, not plus 10, x squared. Let me check the rainbow box again. I'm plugging y equals minus 1, so this should be minus 10. I see, that's why it's different. This should be minus 3x squared minus 10x squared will be 3 minus 10 is minus 7. So it's going to be minus 7x squared plus 17. Find the derivative of that. Minus 14x gives you 0. X gives you 0. Okay, good. Now we need to check all the candidates which are in the domain. The last step, so this was the longest step. The last step goes faster. Step 4. Step 4, just like in calculus 1, you make a list. All the critical points and boundaries. In calculus 1, there were endpoints. In this case, those are borders. So let's find them all. Let's catch them all, like in, you know where. F of 0, 0. Let's find the height of that. F of plus or minus square root of 12 over 5. What was it? Let me check, not to make a mistake. There was a nasty square root. Yeah, square root of 12 over 25. Oh yeah, you could rewrite this as square root of 12 over 5. That's a good point. Well, do you know why plus and minus is fine? Because the original function squaring the x. So the answer will be the same. Only because of that. It's even with respect to x. But actually you're supposed to check both cases. Maybe I'll write it down for you if you want. For the future, just not to make a mistake. And then we need to find the y value for each by plugging into the original. As you can see, these are the same. So plug it into your 3D function to find the height. F at 1, we also get x equals 1. Plug it into the original, gives you minus 5, 8. There were also points 0, 1. There was also point 0 and minus 1. Cannot merge this because it's not even with respect to y. And there was also point 1, 1. So a list. Here's your list. And you just take a calculator and plug into the original function in the rainbow box. For example, at 0, 0 is the easiest one. 0, 0, 0, 0, 9. The first number is 9. That is my height. The second one is 243 over 25. The next output is the same, 243 over 25, because again the function is even. 1 minus 1 and minus 5, 8 gives you 55 over 18. 0 and 1 gives you 17. I just have the notes in front of me, so check everything. Minus 17 for minus 1 and 30 for 1, 1. And now look at your answers and choose the biggest one and the smallest one. In this case, we are asked to find the absolute maximum. I mean, you need to know what this number is and this number is, but it's not 30. So 30 seems to be like the biggest output we found. So this is going to be my absolute maximum. Finally, the answer. These problems are always very time consuming, but it's worth it because it checks your knowledge from calculus 1 and calculus 3 classes at the same time. Answer is, at the point 1, 1, we had absolute maximum height which 30. Pretty cool. So the location of the absolute maximum is 130. The mountain from all other mountains on the restricted domain is located at 1 unit on the x-axis, 1 unit at the y-axis, and 30 units up. So it is over here, right? 1, 1, and 30. Yeah, this is the point. And we checked everything in between and on the edges of that square in 2D. 1, 1, and 30. Very nice. This is the final answer, and check all the calculations and make sure you understand what is happening here. We're checking everything on 2D on the restriction square. How did we do calculus 1, absolute global maximum minimum right now on each case of each line, and so on. It's very tedious but pretty interesting types of problems. Thank you for watching.